Hi, my name is John Baldwin. I'm here to, the title of my talk is ELF Nightmares, GOTS, PLTs, and Relocations, oh my. But hopefully it's actually not quite as scary as the title might indicate. I've been recently doing some work as part of my cherry project involving working with how linkage works inside of ELF. And so this talk isn't really about the work that I'm doing currently as much as it's kind of the background of some of the work that I'm doing currently and a collection of different things that I've learned like 3 or 4 different times over the years. And so it's just kind of a compendium of various things in this space. So I'll start by kind of defining the problem that we're talking about, like the problem we're trying to solve with this set of topics. Then we'll talk about relocations and what those are, different code generation modes that we use in the compiler and the linker to kind of cooperate. Then we'll introduce something called GOT indirection that's used for data variables, and then function indirection for function calls using something called a PLT. Then we'll go back and talk a bit more about code generation modes. And if time permitting, we'll talk about these kind of more esoteric topics, things called copy relocations and canonical PLT entries. And then I do have a slide on indirect functions. But I have to warn you that I think that's slide like 45. So I'm just going to see how far we get. I have a timer to stop me with 5 minutes left. So we'll get how far we get, and I'll post the slides, and hopefully they're readable for the things that I don't make it to. So what problem are we kind of talking about? And roughly it's the question of how do we take symbols, which is how we name things in source code with names, like printf is a name that we as a person understand, and how do we map those? So source code refers to these things by strings, because that's what humans refer to them as. But machine code does not think in terms of strings. And I say, like, machine instructions don't think in terms of strings. They think in terms of addresses. And the way things are named in machine code is addresses. And so the problem we're trying to solve is how do we deal with mapping symbols that show up as names, like printf in the source code and in our brains, and how we kind of map those into the addresses that actually happen at runtime. So I'm going to start off by defining a few terms to give us some shared jargon or lexicon, at least the jargon that I use, so you can parse me when I'm talking. So these are my own rough definitions, and if they're wrong, that's okay. It's just my weird language. You can ignore them afterwards. So I'm going to say that a compiler is a program that translates source code from one language to another. And often, in our case, in kind of the world that we operate in, usually you're translating from something into assembly. For example, with C and C++, you're typically having your compiler translate into assembly. So things like Clang and GCC would fall into this. And then assembler is something that takes assembly as input and it generates what I'm going to call an object file as its output. And the object file contains machine code and the initial value of kind of data variables like globals. And object files, as a rule, even across different formats, even though we're going to mostly focus on ELF today, they're generally split into sections, where different sections can contain different types of data. And a general section usually contains the kind of same type of data. So .text tends to only contain machine code, and .data contains variables. Some examples of this are, well, for the GNU world, the assembler as. So GCC will invoke a separate program to do assembly, whereas Clang tends to actually do all this internally. So Clang normally takes your source code, translates it to an assembly internally, but actually ends up outputting an object file directly without kind of being 2 separate tools. So the next kind of step in the process of getting a binary is something called the static linker. At least that's what I'm going to call it. And a static linker takes multiple object files as its input, and it merges the sections from those object files to generate sections in a new linker output file. So for example, we might take all the .text sections and merge them together into a new kind of larger single .text section in a library or a binary. So we can generate executables or shared libraries, and those executables can either be static or dynamic. Some of the linkers, or the static linkers we see in FreeBSD and other BSDs would be LLD from the LVM project or GNU binutils linker BFD. And then another definition, and this is where it might get more, I'll be more opinionated. A runtime loader is a program that takes some kind of dynamic binary and is responsible for loading it into memory and handling initialization of that program so that it can run. In particular, I like to differentiate linker versus loader to actually mean these two different steps of the static linking as the linker and the runtime handling as the loader. But oftentimes, people will also call the loader the dynamic linker or the runtime linker, and the terms get easily conflated. So in FreeBSD, LDElf.so.1 would be our runtime loader. So let's maybe, given those definitions, kind of restate the problem a little bit more. So converting source code into machine code takes several steps, right? We have to compile it into assembly. We then take that assembly and translate that into actual machine code. And then we have a static linker that kind of glues all the things together. So the machine code is generated by the compiler and the assembler. That's how we get into object files. But we don't actually know the final addresses of symbols until we link. So the object files don't have enough information to actually fully define what the addresses are going to be inside of, for example, the instructions. So the way we get around that, or the way we solve that problem, is part of the job of the static linker, in addition to merging things together to build output sections, is it also patches things in the file that it's generating. So we will patch bits of instructions, like individual fields, immediates inside of instructions, or patch data variables. But now we have a new problem, which is how do we describe that patching? We need some way to think about how we're going to manage this patching in a way to describe the operations that we're going to do. So let's talk a little bit more about the simpler case, and kind of the earlier case, because this stuff has also evolved over time, which is linking a static executable. So for object files, they're effectively all kind of created as if they were going to run at address 0. And they have kind of relative addresses of other things defined in the same object file that all assume kind of a base address of 0. So if you have multiple functions, maybe the first one is at address 0, and the next one is at address whatever the first function's size was, type of thing. As a static linker is taking these multiple object files and combining and merging things together, it effectively rearranges the input section. So you might have an object file that has a text and a data, and another object file that has a text and a data. And the linker is going to take the two texts and glue them together, and then take the two datas and glue them together. And so you can have interleaved output compared to what you got on the input side. So the linker is rearranging all these things. And once the linker has done all this, now it actually has the layout of your final output file. And once it knows the layout of all the relative locations of individual functions and individual global variables, now we can actually compute and assign the final addresses of all these symbols. And once we have these addresses, now we're at the point that we have the information that we can actually go apply all these patches to fix up instructions or fix up initial values of data variables to be aware, because now we have the addresses and we can actually finalize it. And for example, define what the address of printf is when we call it. So let's go back and look at our hello world. So the one thing we need to patch in this case is main is going to call printf. And main lives at some place. Here I've kind of arbitrarily said main sort of lives at 0. And printf lives somewhere else in our address space. And there's a branch instruction that's going to call printf from main. And so the thing that we need to patch is we need to make sure that when we actually call printf, we go to the right address. And so once the linker knows the address of printf, it can patch up or fix up the branch instruction to go to the right place. And this can also be true not just for function calls, but some kinds of global variables. Because if a global variable contains an address, it contains a pointer, then we have to patch those up as well. An example of this that Kirk is somewhat perhaps guilty of would be something like telq head initializer, which if you don't know how telq works, the head pointer is null, but the kind of end of the list pointer actually kind of points to the previous element sort of thing. But so it has a nested non-constant pointer inside of it. So that's static linking. But we also, in our world, do a lot of dynamic linking. So kind of how does that become different when we do dynamic linking? So when we're using shared libraries, things get slightly more complicated because some of the addresses for some of our symbols, we don't actually know at static link time. We actually don't find them out until runtime when we've loaded a shared library into our address space at whatever address the kernel has chosen for us when we call mmap. And so those addresses can't be patched by the static linker because the static linker doesn't know what they are. They're not available. Instead, the runtime loader has to handle patching those addresses in some way so that the program can run. And so instead of being patched in the file in particular that ends up on disk, we have to actually patch those every time we create a process and run your program on the in-memory copy. So back to our hello world example, if printf is not actually statically linked into our binary, but our little hello program is linked dynamically and the C library is in a shared library, then only once we actually have loaded the C library into our address space with mmap and figured out what its address is, that's when the runtime loader can patch the call from main to actually call printf. So this brings us to the next kind of topic we're going to talk about, which are relocations. And the first thing I want to kind of say is, why do we call them relocations? Well, the process in the static linker, think about in particular the static linking case, we're rearranging these input sections as I described, and we kind of interleave things. Well, you can think of that for each of those kind of input functions or input variables, at the end of static linking, we've moved them to an alternate address or relocated them to an alternate address. So because we are relocating things around, kind of coping with the fact that we've moved things around, that's where we get the name relocations from. And relocations come in two different flavors. So the first kind are static relocations. And static relocations are kind of a data structure that the compiler and assembler cooperate to generate. Mostly the compiler does it, but they both kind of cooperate. And those describe to the static linker the patches it should do. And those are intended to be generated by the compiler and consumed by the static linker. And those handle things that are defined at link time. Then a second set, rather, of relocations are dynamic relocations. And the purpose of dynamic relocations are also a similar data structure. These are generated by the static linker when it's building an executable or shared library. And they are used by the runtime loader to manage the patching that's done at runtime. So static relocations they come from the compiler, and they're an input to the static linker. And dynamic relocations come out of the static linker and are an input to the runtime loader. And in ELF, both types of relocations, we actually use the same underlying data structure to describe both of them, which makes life somewhat less complicated. Somewhat. So what do relocations look like in ELF? So in ELF, we have a little struct that has a couple of fields. Some of the things that we have are kind of the location that we're going to patch, which you can think of as the target address. Although in ELF, the way it's encoded, it's actually the offset in the file that is going to be patched. We have a type of relocation, which I'll get into more later about how that's used. In some cases, depending on the type, we have the index of a symbol that we can find in a table to find out what its name is, but we have some notion of a symbol that's related to this, probably somehow like the symbol whose address we're going to use for applying the patch. And then we can have an addend, which is an offset applied to whatever address we get from the symbol, or used in some other cases. And the symbol and the addend can be optional. Then in ELF, we actually have two different structures that can describe a relocation. On some architectures, we use a version called elf_rel. And elf_rel doesn't, in the structure, it includes kind of the first three fields, but it doesn't include an addend. Instead, if there is an addend, it's actually stored in the target location. So the way you handle relocations with elf_rel is if it's a type of relocation that needs an addend, you have to go read the addend out of the place you're going to patch, figure out your computation of the value you're going to store, and then you write the final value back to the location, which means you've destroyed the addend. So you only get to do this once. It's not idempotent. But there's another variation, elf_rel_a, where the addend becomes part of the structure. So the structure gets a little bit bigger, but now the addend is not stored in the target location, it's stored back in the relocation, which means you're not overriding the addend when you actually do your relocation patching. And typically, older architectures like i386 will use this, and newer architectures like ARM64 and x86, 64, and RISC-V, they all tend to use the version with add-ins, because we learned that maybe it was a bad idea to overwrite your thing sometimes. So I mentioned types earlier, and types are a constant kind of set of numbers you could think that map to operations, and they're architecture dependent, so every architecture defines its own set of types. And the type specifies various properties about what you should do for this relocation. It tells you how you're going to calculate the address that you're going to eventually patch into the target location, and also how to store the result. In many cases, you're patching instructions, and you don't want to just take a 32-bit address, in some cases, and overwrite the whole instruction word. Instead, you might have a 12-bit field at some offset within the instruction word you need to write to. And that's part of what the type encodes is not only the computation you're going to do, but how are you going to take that result and store it? And maybe which part of the address you're going to store. We have an example of that coming up. There are some kind of classes of related relocation types. There's also ones that don't quite fit into these, but some common types of relocations are absolute addresses, and these tend to follow a pattern. They all start with R_, but they tend to have ABS at some point in their name. And these tend to take the address of a symbol and add the add-in to it to compute the final address that we're going to store to the target. We also can have relative relocations, which don't get associated with a symbol. They're typically used for things like local private variables. And they're going to take the base address of my executable or shared library, wherever it's been loaded into memory, and use the add-in as an offset relative to the base. So these are basically relative fix-ups to wherever the object file was loaded, or the output file rather. And then you can have PC relative relocations. And in these types of relocations, we're doing a value that's still kind of like an absolute address, but we're going to apply it to something that has the current program counter to hand. And it really wants just an offset relative to the program counter to get to the destination address. So in this case, when we're computing the address we're going to fix up, we take the symbol and its add-in, and then we subtract off the kind of current place that we are, because usually you use this when you're patching an instruction. And the instruction already knows it is using an offset relative to the PC. And these kind of constants are typically, if you look at, I have an example here of a place you can go to see the list of relocations and their kind of the addresses that are computed for RISC-V, and you'll see this kind of annotation used to describe the address calculation formula. So in some cases, you can actually have a single relocation that touches multiple instructions. So in particular, ARX64 and RISC-V are examples of architectures that use multiple instructions to construct an address. x86 doesn't always do this because, for better or for worse, x86 is a variable length instruction architecture. So if you want to load a 32-bit constant, you do. You just kind of make that much more room depending on the opcode you have, and you can patch the full 32-bit or even 64-bit address directly into some location in the instruction. But architectures with a fixed length instruction, like RISC-V and ARX64, well, they have a 32-bit instruction. You can't put 32 bits of address in a 32-bit instruction if you plan to have an opcode somewhere. So you only get to do parts of it. So when you have something like a 32-bit value, you have to split it up into different instructions. And if you do that, every instruction needs its own relocation, because they're going to have to patch multiple things, and so each one gets its own set. So here's an example. We're going to take a very simple C statement, and we're going to come back to this in the future. But in RISC-V, if we're going to return an address of something, in this case just some global named foo, when assembled, it becomes a couple of instructions. This first one is a load upper immediate, which takes the high 20 bits as a kind of immediate constant in the instruction, and we'll store it in the register. And then we do an add instruction, which takes as an immediate a 12-bit field that gets the low 12 bits. So these turn into separate relocations for the upper 20 and the low 12. And the static linker has to know that it's kind of getting, every time it computes the same 32-bit address, but it puts different parts of that address at the different locations in each instruction. All right, yeah, I said that, okay. So how do you look at relocations? Because I spend sadly far too much of my life doing this, at least in the last year or so. So there are a couple different ways you can look at relocations if you'd like, because you have nothing else to do. So readelf minus r is one. It just gives you a global dump of all the relocations in a given file, both static and dynamic. For objdump, you can pass minus r lowercase, and it'll give you only static relocations, and they're actually kind of broken out by section. So you get like a section that has relocations listed, and then all the little relocations for that section and so forth. If you do capital R with objdump, you can get dynamic relocations instead. And then another neat thing that objdump has is when you're doing disassembly with -d, if you pass R along with -d, then it adds little annotations in line with each instruction to show any relocations that are applied to that instruction. And then the way that I often end up using this, like for most of the examples later in this talk, is I use a website called Compiler Explorer, which is a pretty nifty tool if you've not heard of it. You get to type in little snippets of C, and then you get to select a version of a compiler. You can pick all sorts of different versions of Clang or GCC or a few others. And you can pick not only different versions, but different architectures, and you can specify the command line flags, and it'll spit out the assembly, or you have options, for example, to actually compile to an object file and dump the disassembly of the object file. So that's often what I actually use to look at relocations, and it's what I'm going to use for most of the examples in this talk. So we're going to go back to the example we had from before. So this is my return foo, but now I've made it actually compilable, add a little more sugar around it. And we're going to compile it with, so it's RISC-V, using this version of Clang. Turned on O2 so I don't end up with a bunch of assembly instructions that just add clutter. And we'll explain why later, but we're going to do fnopick. And so we get the load up or immediate instruction I talked about, and we can see we've got this kind of thing around foo. So this says that I'm going to do a special relocation of the high 20 bits, and I have the add instruction with the low bits. So that's the assembly you get out of Clang if you ask for the assembly if we're compiling the return foo. But if on Compiler Explorer, you click on this object, or this little option it has of compile to binary object, then it actually compiles all the way to a .o and feeds that .o, or the object file, into objdump minus -dr. So it then disassembles the result and shows you the relocations. So now, this load up or immediate instruction, well now instead of having a reference to foo, the instruction just has a value 0, because that's the value that's going to get patched by the static linker. But we can see that we now have this high 20 relocation against symbol foo. So now we've actually turned it into a relocation for real, not just in the assembly. And similarly, now this one looks kind of weird because the way register move is encoded in RISC-V is an add with 0. Right? You just add 0 to the register to the target. So in this case, the disassembler has said, well, you're adding 0, so you really mean to move. But actually, under the covers, it's still an add instruction, just with a 0 constant that this relocation will fix up. All right. So I'm going to switch gears a little bit. And the next topic I want to talk about are different ways in the compiler we can choose to generate code. And we have 3 main kind of modes we can use to generate code. And I'm going to walk through them in a bit of an order. So the first one is something called position-dependent executables, or PDEs. And this is kind of the oldest version. And it's typically would be used for static executables in libraries, but can also be used for dynamic executables, which gets interesting later on. If you wanted to definitely generate this version, you would use -fnopick with either Clang or GCC to get this type of code generation. Another version are position-independent code, or PIC, which probably many of us have heard of. This is used for shared libraries, and you do -fpic, usually lowercase, some architectures uppercase. Most of them, they don't care which one anymore. I think MIPS is one that cared. We'll talk more about MIPS if we get there. And then lastly, a more recently introduced mode is something called position-independent executable, or PI. That can also, just like PDEs, be used both for executables, static and dynamic, and for static libraries. And the command line flag for it is very similar to PIC. It's just PI. So how did we get 3 different code generation formats? Well, we started off, at least as far as I can tell, with just having static executables and not having dynamic shared libraries. That was a refinement. And so initially we had executables that, when we had virtual memory, were linked to run at a fixed address. So like that's probably what well, I don't know exactly the timeline of BSD that would be, but presumably that's kind of how static executables on at least 4 BSD were. They were on FreeBSD 1 at least. When we added shared libraries, we kind of started off with PDEs as our base and decided, well, how can we add shared libraries to work with the fact that we're used to having these static binaries that are position dependent. So when we do shared libraries, we compile all the things that belong to a shared library with pick. And we link them into a .so instead of a normal kind of binary. But we left executable object files the same. They're still actually PDEs, even though they're dynamically linked. Later, or actually relatively recently, we've actually added the third mode of Pi, kind of largely motivated by ASLR because it wanted the ability to move the executable around in the address space. And it has a couple of implications, if I could speak. There are a couple of implications of switching to Pi. One is you now have to fix up kind of runtime patching of executables the same way you would for shared libraries in Pi, even if they're static, which is part of why FreeBSD doesn't do static Pi binaries currently. And you can kind of think of Pi as a version of PIC that we use for shared libraries, but somewhat optimized. It's kind of a middle ground between PDEs and PIC. Yep.
FreeBSD 1 had A.out, FreeBSD 3 added ELF, FreeBSD 4 added shared libraries.
We had shared libraries with A.out.
We also had shared libraries with A.out, but it wasn't ELF format.
Fair enough. But presumably those, I believe our A.out binaries were still effectively PDE and the libraries were PIC.
Yes, they were.
So some of this, I'm mostly using ELF, but some bits are also applicable to other formats. So what are the things that we had to change when moving from PDE to PIC? What's different about compiling things in PIC? Well, one thing is that shared libraries can be loaded at arbitrarily different addresses. You don't know at link time what address you're going to be loaded at necessarily. So we can't access symbols directly. We don't know what they are. And we're going to have to fix them up. But one thing that we can use, is we know that even if the shared library is located at a different location and address space at any given time, the relative offset between different things inside the same shared library doesn't change. So if we can get the value, some kind of offset inside our shared library, we can find something else within our shared library because we know it's at a fixed offset from that location. And when we're executing inside a shared library, one location we have that is inside our shared library is the current value of PC. So if we have the current value of PC, we can find something else inside of our self. We may not be able to find necessarily like a direct address, so something in the executable or another shared library, but we can find something inside of our self. So, OK. So global variables and functions that are in a different linked object file, like in an executable or a different shared library, we don't know those at link time, but they are known by the runtime loader. So how are we going to get to things that are not inside our self? So I guess I should back up slightly. That means that if we're in a shared library, we need to get to one of our own global variables. We actually could just take an offset to PC to find it. It's more the case, mostly, that we're in a shared library, we need to get to something else. Or we're in an executable, we need to get to something else, like a value in libc. That's when we have to find some other global. So how are we going to do that? So one approach that we could take is just like the static linker, we could patch instructions. So we could use relocations so that when we load something into memory, we could go patch instructions to change the addresses encoded in instructions. But one downside of this, among a few others, is if we start patching instructions, we can no longer share the physical pages for a shared library across multiple processes, because now we're changing it every time in every separate process. So instead, one of the fun things in computer science, you can always solve many problems. Well, you can solve many problems with indirection. So we use that principle here. And instead what we do is that when we have a variable or a function that we're going to access from somebody else, we access it indirectly. The static linker, as in addition to merging things that come from object files, it also kind of creates out of whole cloth a new array of pointers that's called the global offset table, or the GOT. It says offset table, but they're really addresses, they're really pointers. And anytime we're going to access a foreign kind of variable, the compiler knows we're in pick mode, and if it wants to read some variable, instead of trying to read from the address of that variable instead, it says, well, I'm going to generate a load against a GOT entry to get the pointer, and then I have the pointer to the thing, and I can then read the actual variable using the pointer I got from the GOT. And so this requires changes in how we generate code in the compiler. And then the static linker, when it has, in addition to creating the GOT entries, it also generates dynamic relocations that tell the runtime loader what symbols are associated with each GOT entry, so that when the runtime loader loads a binary and initializes it, it knows what addresses or what pointers to put in all these GOT entries so they point to the right things. So let's walk through an example of that. So I have a little function here named foo, and it's going to reference some variable named x that doesn't live inside the same like executable or shared library. So it's got a GOT, and one of the entries in the GOT is for this variable x. So when we first load this executable into memory or this shared library, the runtime loader is going to walk through and process all the ELF relocations it has, which give it instructions on how to patch each GOT entry. So as part of that, we're going to go find, oh, my x, I've done a symbol lookup on x, and it lives over here, some other shared library, we don't care which one, but just somewhere else. And then we'll take the address of x and store it in the GOT. And once we've done that, then now my foo function can access the value of x, because it's going to go read the pointer out of the GOT and dereference the pointer to find the real thing. All right, so now the next little refinement on this. So I mentioned that we can use the GOT to get to foreign symbols, like something that's in another shared library. But it's slightly more complicated than that. So clearly when we have remote symbols, something that lives in some other shared library, we have to use the GOT to get to it, because we have no other way to get to these things that don't live inside of our own shared library. But the compiler doesn't know what symbols might be remote by the time you get turned into an object file. So if you're compiling a given little .c file, for example, inside of libc and you're part of standard I/O, and there's some globals that are part of standard I/O state, it may not be defined in your .c file, but in some other .c file. And as a compiler, you don't know that. You just know I've accessed some symbol. And so I don't know how to get to it, but I have to generate the assembly for the machine code, and I have to decide at that point, am I going to indirect through the GOT? So in practice, and we have another use case, which is sometimes we want the ability, even if a symbol is defined in the same .c file and thus the same .o file, we want the ability to override it. So an example of this is you may want to use a different version of malloc and free inside of libc. You want to use a debugging version of malloc and free with LD preload. Then you need to override all references to malloc and free, including references to malloc and free inside of libc. So instead, what we have in ELF is a notion that some symbols are preemptible and some symbols are not. And a preemptible symbol is any symbol that kind of goes through GOT indirection. Even if it's defined in the same .o file, the same object file, or the same shared library, we're not going to access it directly. We're always going to go through the GOT to find our pointer to access it, because it may point to our version of the symbol, or it may not. So how do we decide which symbols are preemptible? So ELF symbols have a couple of different properties. One of them that's somewhat obvious is something called binding, which defines global symbols versus local symbols. So if you do static int whatever inside a .o file, that ends up being a private symbol that's a local symbol that's hidden by its binding. But there's another property called visibility, and that affects how ELF handles global symbols and kind of what rules we decide of if a symbol is preemptible or not. So by default, if you have the default visibility for a global symbol, then we allow other object files and other output files to see that symbol and take references to it. And it's also preemptible. So another output file, like another shared library, could actually define its own version that takes precedence over the version defined in your shared library. There's also a visibility type called hidden. And with hidden symbols, it's still not a local variable, it's global, meaning that it can be shared perhaps across multiple .o files that were used to build up your shared library, but it's not visible outside of the shared library. And this could be useful for things like, if like in standard I/O and libc, you might have some globals that you need to share among all the .c files that make up standard I/O, but you actually don't want the outside world messing with them. You just need to share them inside your library. So hidden visibility lets you do that. And we even have a little wrapper in cdef.h to let you tag symbols as hidden. And then one that's kind of not, I haven't seen used very much, is a visibility type called protected. Protected is kind of a mix of these two. Protected symbols are, other shared libraries can reference protected symbols, but inside your shared library, you always access it directly without going through the GOT. All right. So we talked about using the GOT to access data. Now let's talk about function calls instead of data, because they're yet another wrinkle on top of this. So we could choose to treat functions just like data. We could decide that we're going to have GOT entries for functions, and anytime you're going to call a function, you go read the entry out of the GOT in your codegen, and then you branch to it. So you do a load and then a branch. But ELF doesn't do that for a couple of reasons. One reason is that many libraries might have a lot of potential remote functions we might want to call that are associated with a lot of GOT entries. If you directly have the compiler always assume it's going to kind of read from the GOT directly and call the function, then every time you would relocate one of these shared libraries, you have to go and populate all those GOT entries. So in particular, think about libc. Libc has references to all sorts of things. But a given program like ls may only use a few of the functions from libc and not all the internal bits that go and call off DNS resolving and stuff like that. So you might spend a lot of time applying relocations for GOT entries that you're never going to call. The other thing that we're going to get into is it turns out static functions compiled with PDE that are dynamic also need a way to call remote functions. And they're already defined to use simple branch instructions. So instead, we make a different choice in ELF. We use something called a procedure linkage table, or PLT, as a way to handle remote function calls. And for what we do with the PLT is for every preemptible function that a given shared library or executable might call, we create a special little stub function, usually only a couple of instructions or like 3 or 4 instructions long, or a thunk in this PLT. And it's an array of these stubs. And every stub function does only a couple of things. It has associated with an entry in a new GOT. We actually have a separate GOT called the PLT GOT, which is different than the other GOT. So we have 2 GOTs now. And the stub function reads a pointer out of the PLT GOT and branches to that. And then every entry in the PLT is associated with a dynamic relocation. Usually it's named a jump slot. And the symbol for that relocation is the name of the function that's associated with this stub. And the target address for the jump slot is to fix up the GOT entry to point to the function we're trying to call. So it turns out, I guess the next way to describe part of PLTs is to solve that first problem we mentioned of not spending a bunch of time fixing up GOT entries, we only fix up PLT GOT entries on the fly the first time a function is called. So to avoid all that overhead, we only do them the first time. So the first entry in the PLT is actually kind of special. It's usually a bit longer. It's not just 2 or 3 instructions. And it's a special kind of thunk called PLT0. And what PLT0 does is PLT0 reads a couple of entries from your PLT GOT, usually at the very beginning. One is a function pointer, and one is some kind of opaque data pointer. And the way the PLT thunks work, the normal stubs, when they're configured at startup, they don't jump directly to the target function. Instead, what they do is they actually jump to this PLT0 stub, and they have, as part of the way PLT stubs are defined, they pass along, usually in some register, the index of the given PLT stub and the whole PLT. So you kind of know which PLT stub you are. Some architectures, you can use the return address to figure this out. On x86, it's actually this little instruction in the bottom of the PLT stub that puts a value in a register. But effectively, we can figure out, when we get into PLT0, which PLT stub you're from. And we're going to, all right. Oh, that's what I'm saying here. Sorry, my brain went further ahead of my slides. So we have the index of the PLT entry, and we have that to hand when we get inside of PLT 0. So this means when PLT 0 runs, it reads these two pointers, and it calls the pointer, the function pointer, passing this data pointer, but also, in some other register, this index. So the function pointer that we're calling gets two things as its input. It gets some kind of data pointer that came from the GOT, and it gets the index to say which PLT stub actually called it, actually is trying to resolve a symbol. So what the runtime loader does, on the kind of backside of this, is the runtime loader initializes those two entries in the PLT GOT to point to a special function that it's going to use to handle resolving PLT symbols, and it stores a data pointer that describes which shared object is trying to make the call. In the case of FreeBSD, this function is usually written in assembly. It's called an RTLD bind _ start, and it is a little bit in assembly that eventually calls RTLD bind in C. And the data pointer points to the obj entry structure, which is a structure that FreeBSD's runtime loader uses to describe each shared library. So we get the pointer to this data structure and the C function that this calls, and we also get the PLT index inside of the RTLD bind function. And we can use that. So when we call this, it takes that PLT index, and to figure out from this obj entry, we know which PLT we're looking at. We can use the index to find the relocation table, find the relocation inside that relocation table, and that tells us what symbol we're looking for and which GOT entry we're going to patch. So we apply the relocation, it fixes up the GOT entry, but then we have one last problem, which is the very first time we were called to jump to like printf or whatever target we were going to. Well, we can't return to the caller and try to have it call again. It's already called us. So when this assembly function returns, it doesn't return to whoever called it. It actually returns by jumping to the function that we're trying to call the very first time. All right, so I have a picture of this that hopefully is better than the wall of text. All right. So we have, in this case, a little dynamic binary. It's going to call printf twice. You'll see why in a second. And we're going to rely on the compiler to not cheat and turn this into puts or combine into a single call, which compilers will do to you because they're our adversary many times. But just pretend like it actually thinks what you think it does. So the output that we would get once we've compiled this and we've linked this into a dynamic binary is we've got a main function, and we have a PLT that has this PLT 0 stub at the beginning, and it has an entry for printf. Which in assembly we tend to call this like printf at PLT. It's how we annotate and distinguish the real printf from the PLT func for printf. And then we've got our PLT GOT, which has got a couple of entries, right? Just like a normal GOT, this is an array of pointers. So when our runtime loader starts up, first it's going, well, right, but back up before that. The way this is kind of linked at static link time is that the branch in main it's going to call printf. Every time it calls printf, it jumps to this printf at PLT. That's going to read the address of printf from this third slot. And that's kind of the way we're finally linked from the static linker. So now let's actually start executing and see what the runtime loader does. So the runtime loader, it maps the binary, the kernel maps the binary actually, and it maps this. And in the runtime loader, we have our TLD bind start over here. And as we're relocating this object, we allocate a data structure. And for the main executable, it's called obj main, if you go dig around in the source code to the runtime loader. And the runtime loader is going to configure these first two entries in the PLT GOT. We have the code pointer that points to RTLD bind start, and we have that opaque data pointer that points to obj main. And the way we process the relocations initially for the PLT GOT, we've changed effectively this third PLT entry actually to jump to PLT 0. And it turns out that's cheaper than the normal relocation we would have to do, even though we have to do a little bit of work. And then, because this binary said it needed libc, we go ahead and map that in, and it has a printf function. Now we're ready to start executing. So what happens the first time we call printf? Well, the first time we call printf, we're going to jump into the PLT stub. Yeah, I should back up a little bit. All right, now it's called printf. So the first time we call printf, we're going to follow jumping to the direct branch instruction going to the PLT. Then the PLT stub is going to read from here a pointer that points to here. So it'll jump into here, and that's actually going to go call this function with passing this data variable And the runtime loader uses it to figure out this is the thing we're trying to change. So then the runtime loader is going to rewrite it to point to here. And then it's going to return. When it returns, it's actually going to call this function. The second time we call the function, and we call branch, well, the second time we actually branch to here just like we did before, but now the value we read from the GOT is the function we directly call to it without taking a detour through the runtime loader. All right, so where am I at? Because now I'm out of time. Okay. All right, well, this is as good a place to pause as any. Well, we'll get to some of the fun stuff. So do you have questions? Do you want me to try to go further into the break?
Well, perfectly clear.
Well, it wasn't perfectly clear to me the first few times I tried to learn this. Does anybody have any questions, or do you want me to keep going, or what would you like? All right. So we'll keep going for a few more minutes. So let's revisit this notion of PDE and PIC and PI and go a little more fancy. So I'm going to have the same little snippet of code. We're going to use Compiler Explorer. And we're going to do a couple of things in this function. We're going to take the address of a global, and we're going to call a function, and both of these are remote. And we're going to look at what assembly we get in each different mode and kind of what relocations we get. And in this case, we're going to stick with x86. We're using GCC, and we're doing, to start with PDE, we're doing fno-pic. So we get a couple of things. We have some kind of boilerplate around managing the stack pointer. But we're going to read, the $x here means we're taking the absolute value of x, kind of encoded as an immediate instruction, and storing it in this register, which gets passed as the first argument. And then we're going to call bar. And the way both of these are encoded, this one is an absolute address, and this is a PC relative branch, but it kind of hard codes the offset that it's going to jump to bar. So what if we compile this as a shared library instead as PIC? Well, now we see the code's changed a little bit. Like this part's the same, these last 4 bits are the same, but these 2 instructions are a little different. Instead of $x, now we're doing a read from a memory location, and the memory location is PC relative. So we're using the PC to find the location of our GOT and reading the address of the value of x from the GOT. And then that's a pointer that in x86 we can kind of read from the pointer directly to, or no, we're getting the address. Never mind, we're just reading the GOT entry directly. So this is reading from the GOT to get the pointer and storing it in the register. And then when we call bar, now we're actually saying we're explicitly going to go through the PLT stub version for bar instead of directly calling the function. So that's the differences we get with PIC. So then, what if we're not doing a static binary, which was the first version I showed of the PDE? What if we're doing a dynamic binary? Well, it turns out the code generation is the same, because PDE is PDE. It doesn't really care if you're static or dynamic. So what if x doesn't live inside my binary? And what if bar is also not inside my binary? It's in a shared library, right? Because the code gen is assumed that it has the address. So with dynamic executables, we have a couple of tricky cases, some harder than others. The first one, the easy one, is how do we handle branches by calling bar from a dynamic executable that's compiled as PDE? And the answer to that was, well, we just use our good old friend, the PLT stub. It's actually what my lazy PLT example did. The linker can add a GOT PLT and a PLT stub, and it can rewrite that branch instruction not to try to call bar, but to call a PLT stub. And that's all good. We're fine and dandy. But the data variable case is a little bit more of a pain in the butt. So how are we going to handle the fact that in my executable at static link time, I have to compute a fixed address to store an instruction for a variable that lives in a shared library, when I won't know what the address of that variable is until I load the binary at runtime? And here we use this thing called copy relocations. And if you don't shudder, it means you haven't worked with copy relocations. And the way a copy relocation works is a static linker reserves space in the BSS of the executable for a new version of x. We're going to call x prime, a copy of x. And at runtime, when the runtime loader loads the binary, it finds the real value of x from the shared library, copies that value over into x prime, and then for all the future lookups, anytime anything, either the shared library or a binary tries to find x, instead we redirect it over to x prime. So what does that look like in practice? So here we have our little binary with foo, and it's going to reference x. And the static linker has created this x prime as a place in the BSS. And then we have a shared library that actually has the real value of x that we, in theory, should be using. And because in pick mode, we know these type of shenanigans can occur. This is part of why we have marked x as a preemptible symbol. Anytime the shared library tries to access x, it actually goes through a God entry to get there. So we have a God entry that tells us the address of x, even for use in the shared library. So as the runtime loader starts up, it's going to copy the value of x when it does a symbol resolution and finds it lives in the shared library over into x prime. And then it's going to store a pointer over in the God entry for the shared library, not to point to the shared library where it really lives, but now to live in this alternate copy over into executable called x prime. And we're going to just pretend like x doesn't exist at this point. It's just wasted memory. That, la, 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 don't believe the symbol table. It does not exist. So that's kind of yucky, especially, it's one thing if this is an int, but imagine more complex data structures. This gets really wonky, and things like alignment, and it can get messy. So let's, how am I on time? When am I supposed to be over, 5:30 or 5:20? Now? Let's be over now, aren't I? All right, I'll try to do function pointers, and then we'll stop. So let's talk about function pointers, because that's another fun case. So we're going to have a little snippet of code again. We're just going to print out the address of fclose. And let's start off with a nice little static binary. And we're going to compile the same way we did PDE before. So again, we have our friend, the $, so an absolute address of fclose. We're going to stick in a register. And then we're going to go jump to printf. Well, that's all fine. Makes sense in a static world. And that's a relative branch to printf. So in pick, when we compile this as pick mode, well, now we know fclose might not live in our same world, so we read it from the GOT. So we're reading the address of fclose from the GOT. That all looks kind of sensible. Now we're going to jump to the PLT stub for printf. So that all seems kind of simple, relatively speaking. But let's think about the dynamic binary case. So we're back in PDE mode. We've compiled it the same way, and we need an absolute address for this function pointer, which again lives in a shared library, and we don't know where it lives. So what absolute address are we going to use for that? And this is another thing that the GNU folks don't have a name for this, but one of the LLD developers has a name that I like called canonical PLT entries. This one's a little interesting too. So what address can we use? It has to be fixed at link time before we load it into memory for the pointer to fclose. Well, we can use the address of the PLT stub in the executable. And that kind of seems okay, right? Because when you jump to the PLT stub, it will resolve and call the real function eventually. So that all seems fine. But C has this little requirement, which is that when you take a pointer to the same symbol, all the pointers to the same symbol need to compare equal. So if the executable is going to get the address of the PLT stub when it takes a pointer, everything else, including any shared libraries like libc in the process, also have to get the address of the PLT stub when they take a function pointer to fclose instead of the pointer to fclose. All right, so now we have a picture of that. So you can think of this as kind of like copy relocations for function pointers. So here we've got our executable, and it has the foo function. It's going to call fclose. And, well, yes. So even though we don't call fclose, we need a function pointer. So we make sure that we're going to create a PLT stub, even though it doesn't get used, just so that we have this God entry that can be the function pointer. Does that make sense? Is it terrifying? And the PLT stub is going to read that entry out of the GOT. That's kind of like before. And then we have libc. And because it's pick, it knows that it has a God entry for fclose because maybe it's been LD preloaded or who knows. So when the runtime loader processes this and it finds the relocation for the God entry for fclose and libc, it's responsible for sending that not to fclose and libc as it normally would, but instead to point to the PLT stub. Which means that any time that libc wants to call fclose via a function pointer, it uses the function pointer from the GOT to jump to the executable to go to the PLT stub, to go into the runtime loader, to then fix this up to point to the real left close, and then jump back into itself. Yeah, that's all. I guess I stepped ahead of myself a little bit. Yeah, see? All right, so I was going to talk about pi. I don't have time to talk about pi. I have many more things, but I need to get to at least the slides at the ends. All right, you can read about that one. All right, I will do this slide, just because MIPS always needs a good kicking. So what about MIPS? So MIPS is a special snowflake architecture in my mind. I think it suffered from being the first to do some of these things. So with MIPS, we don't have dynamic ELF relocations to figure out how we're going to patch our GOT. Instead, we have these kind of implicit rules that we have a single GOT, not a separate PLT GOT, and then we use these tags in the dynamic to split the GOT up into separate regions. We have a region of local symbols. It's kind of like relative relocations, and we always know it's a relative relocation. We just add the base address to whatever's in the GOT. That's it. Then we have a second region called global. And global is split into two pieces. The first part of global are global variables, and the last part of global are PLT stubs. There's a couple of DLT tags that tell us, A, for the global variables, and actually all of them, there has to be a contiguous range of indices in the symbol table that start at this index in the symbol table to tell us what all the symbols are. And the PLT stubs use some portion at the end. We have this tag in the dynamic that tells us when to stop doing global variables, and presumably everything after that will be fixed up lazily. Then the index that comes into the runtime loader from when we're doing the lazy PLT resolution is actually the index into the symbol table. And we take that index and we subtract the starting point of the kind of global region symbol table to get an index into the GOT, except that it's an index relative to this region, so we have to add the base part of that region, and that tells us what index in the GOT we're actually fixing up. More reasons I dislike MIPS. But in particular, because you can't, imagine if you wanted to do some other calculation for some other reason, like Cherry. All this stuff is hard-coded, and it becomes just a giant pain in the butt. The fact that we now have relocations where we can configure how we're going to do behavior and figure out which slot to do it and not have it kind of all this hard-coded gunk, life is better on everyone but MIPS. So when people say, why did you not like having MIPS in the tree? This is one of the reasons I didn't like having MIPS in the tree. All right, this is my last slide. Y'all can read that stuff. Thank you. If you have questions, you can ask.